Good evening, and welcome to another journey into the cosmos. Tonight, we slow down, we breathe deep, and we let the mind drift across the stars. This is science to sleep by, where curiosity meets calm, and where questions larger than life itself guide us into gentle wonder. Tonight's question is simple, yet profound. What is the largest thing in the universe? As we drift together into the depths of space, we will step through cosmic scales, from the smallest glimpse of our world, to the unimaginable structures that stretch across billions of light years. So, settle in, relax, and allow the universe to cradle you into stillness. When we begin to ask what the largest thing in the universe is, we first need to pause and recognize how small we are. It is easy to forget, in the flow of everyday life, that our entire existence plays out on a small rocky world circling an ordinary star. Earth, to us, feels impossibly vast. It takes hours to fly across a continent, days to cross oceans, and months to circle the globe on foot. Yet, in the grand stage of the cosmos, Earth is almost unimaginably tiny. If you were to shrink our planet down to the size of a marble, the sun would become a ball more than 9 feet across, and the distance between them would stretch nearly 100 feet. Already, the scale grows beyond our daily comprehension. The space between Earth and Sun feels empty, but it is a distance filled with energy, light, and gravity binding us in an eternal orbit. As you close your eyes and imagine this distance, try to feel the space. Try to stretch your awareness out beyond the familiar sky. The Earth orbits at just one point on a path billions of miles long. Every second, the Earth travels more than 18 miles through space, carried forward in its cosmic dance. That movement never stops. Day and night we are moving, a small speck tracing a circle around a far greater presence. The sun, in its brilliance, dwarfs Earth to such an extent that 1 million Earths could fit inside it. Already, scale is slipping from our grasp, but the sun itself, that immense golden sphere we depend upon for warmth and life, is not even close to the largest star. It is an average star, a middle-aged fusion engine among hundreds of billions in our galaxy alone. And even as the sun shines, it too is in motion. Together with Earth, the planets, and everything bound to it, the sun is orbiting the center of the Milky Way galaxy at an astonishing speed of about 500,000 miles per hour. Even at such speeds, it will take the sun over 200 million years to complete just one orbit around the galactic core. Imagine that entire eras of life on Earth rising and falling while the sun makes its slow way through the spiral arms of our galaxy. From this perspective, Earth is less than a grain of sand on an endless beach. Think of standing on a shore at night, hearing the waves lap gently against the sand. Now, instead of grains of sand, imagine stars stretching out as far as the eye can see. Every grain is a sun, every grain a potential home for planets, for systems, for worlds beyond number. The Milky Way itself contains around 400 billion stars, and countless more planets orbit them. Our solar system, vast though it seems to us, becomes almost invisible when placed within that sea of light. The human mind was never designed to grasp numbers of such immensity. And yet, we try, we measure, we calculate, we build telescopes to see farther, to pull more light from the sky. We create metaphors, comparisons, scales to make sense of it. But the truth is that the vastness overwhelms language. Even the distances to our nearest neighbors are staggering. The closest star system, Alpha Centauri, lies over 4 light-years away. In the terms of human travel, that is 25 trillion miles. A distance so great that even light, which moves at 186,000 miles per second, takes years to cross. If a spacecraft launched today traveled at the fastest speed ever achieved by humans, it would take more than 70,000 years to reach that star. This is just the beginning of cosmic scale. The moment we step beyond Earth and its moon, the distances explode into incomprehensible lengths. The moon, which feels distant as a glowing silver companion in the sky, is only about 239,000 miles away, a trip of a few days for a spacecraft. But from the moon to the sun is 93 million miles. From the sun to the edge of the solar system, where the solar wind loses its strength against the galaxy, is more than 11 billion miles. Beyond that, the Oort cloud, a vast sphere of icy bodies, may stretch a light year outward. Our solar system is a bubble in space, and even its edge is not the end. It is just the beginning. When we speak of the largest thing in the universe, we are layering these scales on top of one another. Earth is dwarfed by the sun. The sun is dwarfed by larger stars. Stars gather into galaxies. Galaxies gather into clusters. Clusters weave together into filaments of matter stretching across billions of light years. And beyond, there is the observable universe itself, an ocean of space-time expanding in every direction. Each step upward in scale erases the sense of importance we placed on the step before. Each new size, each new number, bends the mind and leaves us quiet, humbled, small. But to be small is not to be insignificant. To recognize scale is to deepen our sense of wonder. Imagine lying beneath the night sky, gazing upward where stars prick holes of light into darkness. The constellations tell us stories, but what they truly represent are reminders of the unfathomable size of the cosmos. That sky is not just decoration. It is a window into endlessness. It is a reminder that we are inside something vast beyond imagination. Our very atoms were forged in the heart of stars billions of years ago, scattered across space, and drawn together again to form us. When we look outward, we are looking back at the history of everything we are. The largest thing in the universe is a question of perspective. But before we even reach galaxies and clusters and cosmic webs, we must first pause and note how small we are in relation to even the first steps. Earth itself, the place where all of human history has unfolded, is a pale blue dot. It is fragile, delicate, and brief against the backdrop of eternity. From the vantage point of space, Earth vanishes into a point of light so small you could cover it with your fingertip. And so the journey begins with humility. To seek the largest thing in the universe is to recognize first the smallest, and to understand the vast ladder of scale that rises above us. Each rung is a new revelation, and each revelation brings us closer to the great cosmic structures that define the visible universe. By stretching our minds to hold these numbers, by reaching outward into the distances, we begin to touch the edges of the infinite, to understand the vastness of the universe. We need to move one step outward from our planet and truly appreciate the enormity of our solar system. It is easy to think of the solar system as the sun, the 8 planets, their moons, and a few asteroids circling in between. In schoolbooks and illustrations, it is often shown as a neat diagram where each planet sits just a short distance from the next. But those diagrams are misleading. The true solar system is a realm so vast that even our imaginations struggle to contain it. The distances between worlds are not short steps. They are gulfs of emptiness, stretches of black space where planets drift like isolated islands in a dark, cosmic ocean. Let us begin with Earth's immediate neighbor, Mars. To travel to Mars at its closest approach, a spacecraft must journey tens of millions of miles. Even light, which crosses the distance from Earth to the Moon in just over a second, takes between 3 and 20 minutes to travel from Earth to Mars, depending on where the two planets are in their orbits. A message sent to a spacecraft on the Martian surface cannot be answered immediately. It must travel through the void, wait for a response, and then return to Earth. That lag is a reminder of how even in our own neighborhood, distances swell far beyond what the human body was ever designed to endure. From Mars, we move outward to the giant Jupiter. Jupiter is the largest planet in the solar system, more massive than all the other planets combined. Its storms rage for centuries, its atmosphere seethes with violent colors and patterns, and its moons form a miniature solar system of their own. If Earth feels small compared to the Sun, it also feels small compared to Jupiter. Our planet could fit inside Jupiter more than 1,000 times. Yet despite its overwhelming size, Jupiter is still just a planet orbiting far from the Sun, bound in the same gravitational chain that holds Earth. To reach it, a spacecraft must travel over 400 million miles, taking years to arrive. Beyond Jupiter lies Saturn, its golden ring stretched wide and thin, shimmering bands of ice and rock circling a world more than 9 times the size of Earth. Saturn's moons are mysterious. Some icy, some shrouded in thick atmospheres. One even boasting liquid seas of methane and ethane. Further still are Uranus and Neptune, the ice giants, their blue-green colors marking the farthest worlds the sun can still warm with faint light. By the time we arrive at Neptune, we are nearly 3 billion miles from the sun, a distance so far that sunlight itself, moving at the ultimate speed of light, takes over 4 hours to arrive. But even Neptune is not the end of our solar system. Beyond it lies the Kuiper Belt, a realm of icy bodies and dwarf planets, where Pluto and Eris drift in frigid orbits. These distant worlds circle the sun slowly, some taking hundreds of years to complete a single revolution. Out here, the sun is no longer a blazing disk. It is a bright star, still brilliant compared to the rest, but no longer overwhelming. The warmth of sunlight has faded, replaced by deep cold, where temperatures drop hundreds of degrees below freezing, and still, beyond the Kuiper Belt, the solar system stretches on. Comets linger in elongated orbits, some diving close to the sun before slingshotting back into the outer darkness. Astronomers believe that far beyond, at a distance tens of thousands of times greater than the gap between Earth and the sun, lies the Oort cloud, a spherical shell of icy bodies that marks the true boundary of the solar system. The Oort cloud may extend out nearly 1 light-year from the sun, meaning that even light itself takes nearly a full year to travel from one edge of this boundary back to the center. This is not just a planetary system. It is a bubble of influence, a sphere of gravity stretching far into the galactic sea. To imagine these distances, we must think in scales beyond our daily lives. If the distance between Earth and the sun, 93 million miles, were reduced to just 1 inch on a scale model, then Neptune would be about 30 inches away, just over 2 feet. That does not sound too great, until we ask, how far would the nearest star be on that same scale? On this shrunken version of the solar system, the closest star, Proxima Centauri, would still be over 4 miles away. The emptiness between solar systems is vast, almost unfathomable. Our nearest neighbors, the Alpha Centauri system, are impossibly distant compared to the space between planets. This realization gives us perspective. The solar system is our home, but it is not a neat collection of orbits tucked close to one another. It is a sprawling system, mostly empty, with distances so enormous that space probes like Voyager 1 and Voyager 2, traveling faster than any human-made objects before them, have taken decades just to reach its edges. Voyager 1, launched in 1977, has finally entered interstellar space, yet even now, it remains within the sun's gravitational influence, still tied faintly to our system after nearly 50 years of travel. At its current speed, it would take tens of thousands of years just to reach the nearest star. The solar system is vast, but it is also fragile. The planets are small compared to the space between them, like dust drifting in a grand hall. Most of the solar system is emptiness, silence, a void that separates worlds from one another. It reminds us that while our planet feels crowded, the greater universe is defined not by fullness, but by space. That space, paradoxically, makes the existence of planets, moons, and life itself even more precious. It is rare to find matter gathered tightly enough to form a world, rarer still to find life, and rarer yet to find intelligent beings who look up at the night sky and wonder about their place within it. As we move beyond the solar system, the scales leap again. What felt unimaginable at first, the 93 million miles between Earth and the sun, becomes almost trivial when compared to the trillions of miles separating stars. The distances between galaxies make even trillions seem small. The solar system, with all its planets, moons, comets, and belts, is just a speck, almost invisible when set against the canvas of the galaxy. And yet, it is here, within this small speck, that life has flourished, that consciousness has arisen, that questions like these can be asked. The solar system is both a cradle and a boundary. It holds us, it shapes us, but it also humbles us. To step beyond it is to enter the interstellar medium, the space between stars, where clouds of gas and dust float for light years, waiting to be pulled together into new stars and new worlds. And in that vastness, we realize that even the solar system, with all its enormity, just the beginning of a much larger story. A story that stretches outward into the galaxy and beyond. A story that connects us to structures so vast they cannot be drawn or pictured on any human scale. If the solar system gives us the first glimpse of vastness, then stars reveal to us the true range of cosmic scale. For most of human history, stars appeared as tiny pinpricks of light, scattered across the night sky. They seemed eternal and changing, points of brilliance set into the heavens. But what we now know is that each of those points is not small at all. Each one is a sun, burning with nuclear fire, radiating immense energy across unfathomable distances. And when we compare them to our own sun, we find that many stars are not just larger, but so gigantic that our sun looks like a grain of sand beside a mountain. Our sun is classified as a G-type main sequence star. It is steady, stable, and about average compared to most stars we know. It spans about 864,000 miles across, which to us feels enormous. 1,000,000 Earths could fit inside it, and its light powers all life on our planet. But in the grand catalogue of stars, the sun is neither small nor large. It sits comfortably in the middle, ordinary among hundreds of billions. When astronomers turn their gaze outward and study stars across the galaxy, they find some that are smaller than Earth itself, and some that stretch across hundreds of millions of miles. Let us begin with the giants. One of the largest stars ever measured is called Scuti, a red supergiant located about 9,500 light-years away. Scuti is so immense that if it were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Our Earth would be swallowed within its burning layers, along with Mercury, Venus, Mars, and perhaps even the asteroid belt. It is difficult for the mind to comprehend this size. A star so wide that the light takes more than an hour to travel from one side to the other. A sphere so bloated and extended that our sun looks like a tiny dot beside it. And yet Scuti is just one of many. Other supergiants, like Canis Majoris or Stephenson 2-18, rival or even surpass it in size. These stars defy imagination. They are vast furnaces, fusing elements deep in their cores while their outer layers expand outward into space. Tenuous and unstable, glowing with a dim, ruddy light. The life cycle of these giants is short compared to stars like our sun. The more massive a star, the faster it burns through its fuel. A star like Scuti might last only a few million years before collapsing in a spectacular supernova, scattering its material into the galaxy. The sun, in comparison, will live for about 10 billion years, quietly shining for eons, before swelling into a red giant and gently shedding its layers. In this way, we see that size comes with sacrifice. The largest stars are brilliant and powerful, but their lives are brief and violent. They live fast and die young, leaving behind black holes or neutron stars as remnants of their cosmic fury. Stars like these give us perspective on what large truly means. To stand on Earth and look at the sun feels overwhelming. The sun dominates our sky, its light defining day and night, its heat determining the very possibility of life. Yet the sun is but a small ember compared to the blazing titans scattered across the galaxy. Imagine trying to visualize the surface of a supergiant star. It would not appear sharp or clear. Instead, it would be a roiling, boiling mass of plasma, convecting in vast currents. Storms and swirls would rise up, larger than our entire planet. The very texture of the star's surface would dwarf continents, mountains, and oceans. One flicker, one eruption, could release more energy than Earth has ever known. But not all stars are giants. Many are smaller, dimmer, and more numerous. Red dwarfs, the smallest main sequence stars, make up the majority of stars in the Milky Way. These stars are often only a fraction of the sun's size, and many burn so dimly that even our most powerful telescopes struggle to see them. Yet because they consume their fuel slowly, they live for trillions of years, for longer than the current age of the universe. Compared to these small stars, supergiants feel like rare exceptions, brief outbursts of grandeur in a galaxy otherwise dominated by small, steady, unassuming stars. This contrast between the largest and the smallest reveals the staggering diversity of stars, a spectrum of size and power that stretches far beyond what our imaginations expect. The scale of stars also changes how we think about distances. A star like Stephenson 2-18, another contender for the largest known star, is estimated to have a radius more than 2,000 times that of the Sun. Its volume is so large that if you tried to fly around it in a jet traveling at 500 miles per hour, it would take you over 1,000 years to complete the journey. That comparison strips away the numbers and grounds the scale in human experience. We measure miles and hours in our daily lives, but stretched into the cosmos, those measurements expand into something almost unrecognizable. These supergiants are not alone in their immensity. They often exist in clusters, regions of space where stars are born together from vast clouds of gas and dust. In these nurseries, the largest stars form and blaze brilliantly, shaping their environments with intense radiation and stellar winds. They carve cavities in the gas clouds, triggering further star formation, setting into motion cycles that ripple across light years of space. The presence of these giants affects entire regions of the galaxy, their sheer size influencing the lives and fates of countless other stars. As we drift deeper into this thought, consider the nature of scale itself. Earth, tiny compared to the Sun. The Sun, tiny compared to Uy-Scuti, tiny compared to the galaxy. Each step stretches our comprehension further and further. Each new level reveals that what once felt infinite is just another point on a ladder reaching upward into boundlessness. The stars remind us of this at every turn. They are markers of scale, glowing beacons that both dwarf us and connect us to the universe. They remind us of the forces that built us, the nuclear fusion that created the elements in our bones, the carbon in our cells, the iron in our blood. Without the giants, there would be no heavy elements, no planets, no life. And so, when we ask what the largest thing in the universe might be, stars give us the first true taste of immensity. They are not the largest structures, but they are the most immediate way to feel scale. A single supergiant can redefine our sense of size and distance. It can stretch our minds until numbers lose meaning, and we are left only with awe. To look up at the night sky and know that hidden among those twinkling points are stars so vast that our solar system would disappear within them is to touch something beyond comprehension. It is to feel the weight of the infinite pressing gently on our imagination, encouraging us to keep reaching outward into the unknown. After standing in the presence of stars, both ordinary and supergiant, the next step in scale carries us to their gatherings, their cradles, and their collective formations across space. Stars rarely live in solitude. They are born in groups, from immense clouds of gas and dust, and many remain bound together for millions or even billions of years. To appreciate what a star truly is, one must also appreciate the clusters they belong to, and the nebulae from which they arise. These structures are not single points of light, but vast, shimmering fields of brilliance, shaped by gravity, radiation, and the endless dance of creation and destruction. When we look through a telescope at the Pleiades, often called the Seven Sisters, we see one of the most familiar star clusters in the night sky. To the naked eye, it appears as a small group of bright stars in Taurus, but in truth, it contains hundreds of stars bound together, drifting through space like a family. The Pleiades are relatively young, formed within the last 100 million years, and their stars still shine hot and blue. The faint haze of reflection nebulae surrounding them is the last remnant of the cloud that gave them birth. This small example hints at the nature of star clusters, collections of suns, each perhaps with planets of its own, traveling together across the galaxy. Their clusters are older, denser, and even more remarkable. Globular clusters, such as Omega Centauri or 47 Tucani, are ancient cities of stars, each containing hundreds of thousands to millions of stars tightly packed into a spherical shape. They orbit the Milky Way like companions, hanging in its halo, relics of the galaxy's earliest days. Imagine standing on a planet within one of these clusters. Instead of a night sky scattered with a few thousand visible stars, you would look upward into a dome blazing with tens of thousands of lights, each so close that it outshines even the brightest stars of our current sky. These clusters compress the majesty of the cosmos into a single view, overwhelming the senses with the density of their brilliance. But even globular clusters are only a glimpse of what lies ahead. For every star cluster, there is a story of origin, and that story begins in nebulae, vast, diffuse clouds of gas and dust, spanning light years across. Nebulae are stellar nurseries, regions where gravity gathers matter until it collapses, igniting new stars in the process. The Orion Nebula, visible even to the naked eye as a small smudge in Orion's sword, is one of the most active star-forming regions near us. Through a telescope, it reveals itself as a glowing cloud of hydrogen gas, illuminated by the newborn stars inside it. Within this nebula lies the Trapezium cluster, a tight group of massive, young stars whose radiation lights the entire region. They are less than a few million years old, cosmic infants by stellar standards, and their energy sculpts the surrounding gas into intricate shapes, pushing it outward, eroding cavities, and triggering further waves of star birth. Some nebulae are quiet, cold, and dark. They hide stars still forming within their depths, cloaked in dust that blocks visible light. The Eagle Nebula, famous for its pillars of creation, shows immense towers of gas and dust where new stars are igniting. Each pillar spans light years, yet they are only small parts of the greater cloud. Within these towering shapes, stars the size of our sun or larger are taking form, drawing matter inward until nuclear fusion begins. To observe such a region is to witness creation itself. Frozen in light years of scale, other nebulae are remnants of stars that have already died. The Crab Nebula, for example, is the expanding shell of gas left behind by a supernova observed on Earth nearly 1,000 years ago. At its center lies a neutron star, a collapsed core spinning rapidly, sending out beams of radiation. The nebula glows with the energy of its past explosion, a reminder that the life and death of stars are not isolated but part of the cycle that shapes galaxies. Planetary nebulae, though smaller, tell a similar story. These are the shells of gas shed by stars like our sun in their final stages, glowing softly as their cores cool into white dwarfs. They show us that nebulae are both cradles and graves, beginnings and endings, linked by the forces of time. The scale of these formations stretches our imagination. A single nebula may span dozens to hundreds of light years. The Tarantula Nebula, located in the Large Magellanic Cloud, is one of the most massive star-forming regions known, over 1,000 light-years across. Within it lies R136, a cluster of some of the most massive stars ever discovered, each dozens to hundreds of times the mass of the Sun. This nebula is so powerful that its combined energy influences the entire dwarf galaxy it inhabits. When we imagine the largest things in the universe, we must consider that even structures like these are still only small patches within the greater cosmic web. Yet they remind us how stars are not isolated events, but products of immense collective processes. Star clusters and nebulae also help us appreciate the timescales of the cosmos. A nebula may last millions of years, but eventually, its gas will either form stars or be blown away, leaving behind only the cluster of suns it created. Over billions of years, those clusters may drift apart, their members scattering into the galaxy, becoming lone wanderers once more. The Pleiades, for example, will not remain bound forever. Its stars are already spreading apart, and in time, it will dissolve into the background of the Milky Way. Globular clusters, on the other hand, have survived for over 10 billion years. Their stars tightly bound by gravity. They are older than our Sun, older than Earth, ancient witnesses to the galaxy's formation. When we place ourselves within this picture, we begin to understand how connected everything is. The Sun itself was likely born in a star cluster, surrounded by sibling stars that have since wandered across the galaxy. Somewhere out there, far away, are other stars that were born from the same cloud as our sun, carrying with them the same chemical signatures, kin in the vastness of space. Our solar system is not an isolated event, but the result of cycles that began in nebulae long before Earth ever existed. These star clusters and nebulae, immense as they are, remind us that scale is both a matter of size and of number. A cluster can hold millions of stars, each with its own story, its own system of planets, its own potential for life. A nebula can span hundreds of light years, its tendrils of gas twisting in ways both delicate and colossal. They are cosmic art forms, painted across the galaxy in colors our eyes can only partly see, but which telescopes reveal in haunting beauty. The largest things in the universe dwarf even these, but clusters and nebulae are where we first feel the power of many gathered into one. A star alone is vast, but 100,000 stars shining together, or a nebula glowing across light years, brings us into a new scale of immensity. They are stepping stones upward into the infinite, bridges between the singular and the collective, showing us that in the universe, greatness often comes not from one, but from many bound together by gravity and time. When we step beyond the clusters of stars and the glowing arms of nebulae, the universe begins to reveal itself in its grandest artistry. Stars do not simply drift alone through space, nor do clusters float forever in isolation. They are bound together in immense systems, families of billions upon billions of stars, held by the invisible glue of gravity. These colossal structures are galaxies, and to even begin describing them is to attempt to measure infinity itself. A galaxy is not just a collection of stars, but a cosmic city complete with planets, dust, nebulae, black holes, and the unseen presence of dark matter, all orbiting around a central gravitational anchor. It is here, in the realm of galaxies, that the scale of the universe takes its next breathtaking leap. Our own galaxy, the Milky Way, is the best place to start. When you look up on a clear night and see the faint band of hazy light stretching across the sky, you are looking edge on into its sprawling disk. That glowing path is not a single cloud, but the combined light of hundreds of billions of stars, smeared together by distance. The Milky Way is about 100,000 light years across, which means a beam of light, moving at the ultimate speed limit of the cosmos, takes 100,000 years to travel from one edge to the other. To put that in perspective, the entire span of recorded human history would not even cover 1,000th of that journey. The scale is staggering, and yet our galaxy is only one among trillions. The Milky Way is a barred spiral galaxy, its stars arranged into curving arms that wind around a central bulge. At its core lies a supermassive black hole called Sagittarius A, containing the mass of about 4 million suns. Around this dark heart, the galaxy spins. Stars, gas, and dust orbit the center like dancers in a cosmic ballet, their motions governed by gravity. Our sun, along with Earth and the entire solar system, takes about 225 million years to complete a single orbit around the galaxy. That means in the 4.5 billion years since the sun was born, it has circled the Milky Way fewer than 20 times. Every living creature that has ever existed on Earth has done so while the planet sails on this endless galactic journey. If the Milky Way alone feels immense, consider our nearest neighbor, the Andromeda Galaxy. Andromeda is even larger, stretching more than 220,000 light years across and containing perhaps 1 trillion stars. It is so massive that its gravitational pull is drawing the Milky Way and Andromeda closer together. In about 4 billion years, the two galaxies will collide, their stars passing by one another like a storm of glowing fireflies. Though individual stars are so far apart that direct collisions are rare, the merging of gas clouds and gravitational forces will trigger waves of new star formation, reshaping both galaxies into one larger elliptical system. This cosmic event will happen long after humans are gone, but the knowledge of it connects us to the deep future of the universe. Galaxies come in many forms beyond spirals. There are elliptical galaxies, smooth and rounded, lacking the delicate arms of spirals. These often contain older stars and can be enormous in scale. Some dwarf galaxies are small, containing only a few billion stars, while others grow into giants. Among the largest ever observed is IC 1101, an elliptical galaxy more than 6 million light-years across. To compare, the Milky Way is 100,000 light-years wide. IC 1101 is 60 times larger, containing possibly 100 trillion stars. If the Milky Way were a single bright island in the dark ocean of space, IC 1101 would be a vast continent, stretching so far across that entire clusters of galaxies seem small beside it. The diversity of galaxies shows us that size and shape are not fixed, but the result of history and environment. Some galaxies are twisted into irregular forms by collisions. Others are stripped of their gas, leaving them quiet and dim. Some are bursting with star formation, glowing brightly with blue, young stars, while others are hushed, their ancient populations glowing faintly red. Across the observable universe, galaxies are the fundamental building blocks of structure, and yet each one is a cosmos of its own. Inside a galaxy, the complexity only deepens. Between stars lie immense regions of gas and dust, where new stars are born. Black holes of various sizes lurk, feeding on matter, and sometimes erupting with jets that extend thousands of light years. Supernova explosions seed the galaxy with heavy elements, enriching the interstellar medium so that new generations of stars and planets can form. Gravity shapes everything, but it is not the only force at play. Radiation, magnetic fields, and even the mysterious influence of dark matter all weave together the fabric of galactic life. The scale of galaxies also reshapes how we think of light. The light from the Andromeda galaxy, visible to the naked eye as a faint smudge, has traveled more than 2 million years to reach us. When you look at it, you are seeing Andromeda as it was long before humans walked the Earth. Light from galaxies at the edge of the observable universe has been traveling for over 13 billion years, nearly the entire age of the cosmos. Galaxies are not just places in space. They are time capsules, carrying with them the history of creation itself. To look at a galaxy is to peer into the past, to witness moments frozen by the finite speed of light. If you could float outside the Milky Way and look back at it, you would see a spiral galaxy glittering against the darkness, its arms curling gracefully, its core shining bright, and you would see it as one of countless others. Through telescopes like Hubble and the newer James Webb Space Telescope, astronomers have revealed the universe as a tapestry of galaxies, stretching outward in all directions. What once seemed like empty blackness is filled with light, each point another Milky Way, another Andromeda, another IC 1101, carrying with it billions of worlds. The universe is not a void but a sea of galaxies, each an island of stars. The sheer number of them is difficult to comprehend. Current estimates suggest there are at least 2 trillion galaxies in the observable universe. 2 trillion cosmic cities, each containing billions or trillions of stars, each with planets, each with potential histories unfolding across billions of years. The scale is so vast that even the word large loses meaning. When we speak of galaxies, we are no longer counting stars or distances. We are speaking of structures so grand that our place within them feels both infinitesimal and miraculous. And yet, galaxies themselves are not the final step. They gather into clusters, and those clusters into superclusters, and those into filaments stretching across cosmic space. But even before we climb to that level, galaxies themselves are among the greatest marvels of the cosmos. To stand beneath the night sky and understand that every star you see belongs to just one galaxy, our own Milky Way, while millions more shine invisibly beyond, is to feel the immensity of the universe press gently into your mind. Galaxies are not just large, they are the foundation of cosmic scale, the vast containers of light and matter that make up the visible universe, the structures that carry the story of existence forward through time and space. If galaxies are the great cities of the universe, then galaxy clusters are sprawling metropolitan regions, binding together hundreds or even thousands of these cosmic cities into one vast community. The scale here defies the imagination. A single galaxy already feels incomprehensibly large, filled with billions of stars, yet galaxy clusters bring together entire collections of galaxies into a single gravitational embrace. They are the next level of cosmic architecture, and their immensity reveals a universe woven together, not by isolated pieces, but by structures of staggering unity. At the heart of a galaxy cluster lies gravity, an invisible hand holding together galaxies, stars, gas, and dark matter across millions of light years. This gravity does not come from a single massive object, but from the collective mass of everything inside the cluster. That includes the galaxies themselves, the enormous pools of hot gas that lie between them, and a mysterious ingredient that makes up most of the weight: dark matter. The galaxies we see, glittering like fireflies in space, are only a fraction of the whole. The majority of the mass is hidden, detectable only through its pull on the visible matter. One of the most famous galaxy clusters is the Virgo cluster, located about 55 million light-years away. It is the closest large cluster to us, and our own local group of galaxies, including the Milky Way and Andromeda, is slowly being drawn toward it. The Virgo cluster contains more than 1,300 galaxies, bound together across a region more than 10 million light-years wide. When astronomers peer at Virgo through telescopes, they see a rich mixture of galaxy-type spirals, ellipticals, irregulars, each one alive with stars, nebulae, and black holes, yet each one part of a greater whole. But Virgo is small compared to the giants. The Coma cluster, for instance, lies about 320 million light-years away and contains over 1,000 large galaxies, spanning more than 20 million light-years across. It is a city of galaxies on a truly cosmic scale. And beyond even this are the greatest clusters known, such as the El Gordo cluster, which translates to the Fat One, discovered in the distant universe. El Gordo is not only massive, but also extraordinarily hot, with gas inside it reaching temperatures of hundreds of millions of degrees. It is so enormous that the galaxies within it are only the shining ornaments on a structure largely made of invisible matter and searing plasma. These clusters are not static. They are dynamic arenas of cosmic interaction. Galaxies within them move at incredible speeds, often thousands of kilometers per second, pulled by the deep gravity of the cluster. As they travel, they sometimes collide or merge, triggering bursts of star formation or reshaping their structures. The hot gas that fills the space between galaxies, known as the intra-cluster medium, is so vast and dense that it outmasses the stars themselves. When galaxies plunge through this medium, their gas can be stripped away, quenching their ability to form new stars and leaving them as quiet, barren systems. Galaxy clusters also serve as natural laboratories for one of the universe's greatest mysteries: dark matter. The visible galaxies and hot gas in a cluster cannot account for the total mass needed to hold it together. Instead, most of the weight is in an invisible form that interacts gravitationally, but not with light. One of the most famous pieces of evidence for dark matter comes from the Bullet cluster, a pair of galaxy clusters that collided hundreds of millions of years ago. In this colossal event, the hot gas clouds slowed and heated up, while the galaxies themselves passed through relatively unaffected. By mapping the gravitational lensing, the bending of light from background galaxies by the cluster's mass, astronomers discovered that most of the matter was not in the hot gas or the galaxies, but in something unseen. This observation gave some of the clearest proof that dark matter is real and dominates the universe's structure. Gravitational lensing itself is one of the most awe-inspiring effects of galaxy clusters. According to Einstein's theory of general relativity, massive objects bend space and time around them, curving the path of light. Galaxy clusters, with their immense gravity, can act like giant cosmic lenses. They bend and magnify the light from galaxies lying far behind them, creating arcs, rings, and multiple images of the same object. This natural magnification allows astronomers to see galaxies so faint and distant that they would otherwise be invisible. Through the lensing power of galaxy clusters, we are peering into the very early universe, glimpsing galaxies forming only a few 100 million years after the Big Bang. The sheer size of galaxy clusters also changes how we think about time. These structures take billions of years to form, slowly drawing in galaxies and gas through the pull of gravity. What we observe today is the result of a process that began almost as soon as the first galaxies appeared. Clusters grow by merging, swallowing smaller groups and clusters in events that release more energy than any other process in the universe since the Big Bang. When two massive clusters collide, shockwaves ripple through the hot gas, heating it further, while dark matter halos pass through one another, merging into even larger structures. These collisions unfold over hundreds of millions of years, an epic slow-motion dance on scales almost too vast to conceive. To appreciate their immensity, consider that the Milky Way, large as it is, becomes almost insignificant when placed inside a cluster. In the Coma cluster, for example, our galaxy would be just one among thousands, circling within a region so large that even light would need tens of millions of years to cross it. The distances between galaxies, though smaller than those in empty space, are still so vast that they emphasize the scale of emptiness as much as the scale of fullness. And yet, held together by gravity, the cluster is a single entity, a cosmic metropolis whose boundaries extend farther than the human mind can easily grasp. Clusters also play a role in shaping the future of galaxies themselves. A galaxy entering a cluster may be transformed by its environment. The dense gravitational tides can distort its shape, while interactions with other galaxies can trigger starbursts or tear stars away to drift in the cluster's intergalactic space. In fact, galaxy clusters are filled not only with whole galaxies, but also with a population of wandering stars stripped away during encounters, forming a diffuse glow that permeates the cluster, like faint starlight smeared across the night sky. From a cosmological perspective, galaxy clusters are among the largest bound structures in the universe. Larger arrangements exist, the superclusters and filaments of the cosmic web, but these are not gravitationally bound in the same way. Clusters represent the maximum scale on which gravity alone has gathered matter into a stable system. Beyond them, expansion of the universe takes over, stretching space faster than gravity can reel it back in. That makes galaxy clusters not just enormous, but also unique, the pinnacle of gravity's ability to sculpt matter into coherent structures. Astronomers study clusters not only to understand galaxies, but to probe the history of the cosmos. Because clusters grow over time, their abundance and distribution reveal information about how the universe itself has expanded. Observing clusters at different distances is like reading the universe's diary, page by page, across billions of years. They are cosmic fossils, recording the interplay of matter, and dark energy through the vastness of time. The human mind strains to imagine what it would be like to float within a galaxy cluster. You would be surrounded, not by one great spiral like the Milky Way, but by hundreds of glowing beacons scattered across space. Each galaxy, a vast island of stars, would hang suspended in the darkness, moving in its orbit around the cluster's center. Between them would be not silence, but a thin, hot plasma, stretching invisibly across the void, its X-ray glow detectable only to sensitive instruments. Above all would loom the invisible presence of dark matter, the unseen architecture holding the whole together, shaping the paths of galaxies, and bending the light of distant worlds through its gravity. Galaxy clusters remind us that the universe is not simply big, but intricately organized on scales that defy intuition. They are the universe's grandest communities, uniting galaxies into structures so large that even the concept of distance falters before them. They show us a cosmos where gravity, invisible, yet irresistible, sculpts matter into forms that stretch across millions of light years, weaving together the story of galaxies, stars, and worlds into patterns far larger than any single system could ever contain. When you take a step back from the individual galaxies, and even from the vast clusters that bind them together, another pattern begins to emerge. The universe reveals itself not just as a collection of isolated clusters floating in the void, but as an intricate tapestry woven from threads of unimaginable scale. These threads are superclusters, the largest coherent assemblies of galaxies in the cosmos, stretching across hundreds of millions of light years. They are not simply clusters of galaxies, they are clusters of clusters, immense gatherings that dwarf anything we might call large within human experience. If a galaxy cluster is a city of galaxies, then a supercluster is a continent, sprawling and interconnected, shaping the very geography of the observable universe. The first step in grasping what a supercluster is comes from understanding scale. A single galaxy like the Milky Way contains a few 100 billion stars and spans about 100,000 light years. A galaxy cluster, like the Virgo cluster, brings together thousands of galaxies across tens of millions of light years. But a supercluster is vastly larger still, reaching sizes of 100 to 500 million light years or more. These are not merely chance groupings of galaxies. They are structures sculpted by gravity, dark matter, and the expansion of space itself, forming filaments and walls that connect across the universe like an immense web. Our own home, the Milky Way, is part of this grander architecture. We belong to the local group, a small cluster of galaxies, which in turn is part of the Virgo supercluster. This supercluster spans about 110 million light years and contains thousands of galaxies bound together in groups and clusters. But even Virgo is not the end of the story. In 2014, astronomers discovered that Virgo itself is just one small piece of an even larger system, a vast supercluster named Laniakea, meaning immense heaven in Hawaiian. Laniakea stretches across 520 million light years and contains around 100,000 galaxies. Our entire galactic neighborhood, everything we see in the night sky, everything humanity has ever known, is just one tiny corner of this colossal structure. The immensity of Laniakea is difficult to visualize. Imagine starting at one edge of this supercluster and traveling at the speed of light. It would take you 500 million years to cross it from end to end. Along the way, you would pass countless galaxy clusters, each itself containing hundreds or thousands of galaxies, each galaxy holding billions of stars and potentially trillions of planets. The sheer number of worlds enclosed in such a structure exceeds comprehension. And yet Laniakea is just one of many. The observable universe contains countless superclusters, linked together into even greater patterns that hint at the ultimate design of cosmic structure. What makes superclusters especially fascinating is that they are not stable objects in the way galaxy clusters are. While a cluster is gravitationally bound, meaning its galaxies will remain together for billions of years, superclusters are more loosely connected. They are regions where matter is denser than average, where gravity has drawn galaxies into vast concentrations, but they are also being stretched by the expansion of the universe. In time, many of the galaxies in a supercluster will drift away from one another, pulled apart by dark energy's relentless push. Superclusters, then, are not permanent fixtures, but temporary arrangements in the long story of cosmic evolution. They represent the largest scale on which gravity has managed to partially overcome the universe's expansion. Beyond that, cosmic acceleration dominates, tearing space apart faster than gravity can hold it together. The structures of superclusters can be breathtakingly intricate. They are not simple spheres of galaxies. Instead, they form elongated shapes, walls, and filaments, with vast cosmic voids between them. The Sloan Great Wall, discovered in 2003, is one of the most spectacular examples. This colossal structure spans about 1.4 billion light-years in length, a vast chain of galaxy clusters forming one of the largest features ever observed in the universe. Later surveys revealed even greater structures, like the Hercules Corona Borealis Great Wall, stretching more than 10 billion light-years across. Though its true nature is debated, such discoveries suggest that the universe is stitched together by threads and sheets of galaxies on scales that defy ordinary language. To see these immense patterns, astronomers map the positions of millions of galaxies across the sky. When plotted in 3 dimensions, these galaxies reveal not a random scatter but a striking design. Clusters link into filaments, filaments into walls, and walls surround great voids, regions nearly empty of galaxies. The result is a cosmic web, a lattice-like structure spanning the observable universe. Superclusters are the brightest threads in this web, glowing strands where matter has concentrated most intensely. The image of a spiderweb stretched across billions of light years is not metaphor but reality, a physical description of how matter ranges itself under gravity and dark matter's guidance. The origin of superclusters traces back to the earliest moments after the Big Bang. The universe began with tiny fluctuations in density, slight differences in how matter was distributed. Over billions of years, gravity amplified those small differences, pulling matter together into galaxies, clusters, and eventually superclusters. The cosmic microwave background radiation, a faint afterglow from 380,000 years after the Big Bang, still shows those initial variations. From those seeds grew the largest structures we observe today. Every supercluster is, in a sense, a fossil of those ancient ripples in the newborn universe. For us as observers on a small planet orbiting an average star in the Milky Way, the existence of superclusters is both humbling and awe-inspiring. They remind us that our galaxy, immense though it is part of a local group. That group is part of Virgo. Virgo is part of Laniakea, and Laniakea itself is just one thread in the grand cosmic web. Our place in the universe is at once infinitesimal and connected to a structure so vast that it challenges the limits of human imagination. Superclusters also raise questions that go beyond their physical description. What lies beyond the observable universe? Are the patterns we see, filaments, walls, and voids, truly representative of the cosmos at larger scales? Or is our visible universe just one patch of a greater whole, with structures so vast they stretch beyond even light's ability to reach us? Some scientists wonder whether there are limits to how large structures can grow, or whether the universe's expansion has frozen the cosmic web into its final form. Others explore whether the arrangement of superclusters hints at deeper laws of physics still undiscovered. Even more profound is the role of dark energy in shaping their fate. As the universe expands at an accelerating pace, driven by this mysterious force, many galaxies in our supercluster will slip beyond our cosmic horizon. In the far future, distant regions of Laniakea will no longer be visible, their light stretched away faster than it can reach us. Superclusters, then, are not eternal monuments but fleeting patterns, existing for a cosmic moment before fading into isolation. The story they tell is one of both creation and impermanence, a reminder that even the largest structures in the universe are subject to change. And yet, for all their immensity, superclusters remain bound to human curiosity. We map them, we name them, we trace their outlines across the night sky. We look outward into their endless reaches, not only to understand where we are, but to feel the scale of the universe pressing gently against the limits of our imagination. Superclusters are not just large, they are the grand architecture of the cosmos, the bridges between galaxies, the glowing threads of the universe's web. They remind us that space is not empty but richly structured, filled with connections that stretch across billions of light years. To gaze into them is to glimpse the universe as a living design, vast beyond words, yet profoundly real in every glowing thread of starlight. At the grandest scale the universe allows us to see, beyond galaxies, beyond clusters, beyond even the sprawling superclusters that stretch for hundreds of millions of light years, lies something even more breathtaking. When astronomers map out the positions of galaxies across the sky, when they step back far enough from the cosmic canvas, an extraordinary pattern comes into focus. The universe is not random, not scattered like grains of sand thrown into the wind. Instead, it arranges itself into a vast interconnected structure that resembles a web, stretching across the observable cosmos. This is the cosmic web, the largest structure known in the universe. A network of filaments, nodes, and voids that extends for billions of light years, shaping the very architecture of existence itself. The cosmic web is not a structure in the ordinary sense, like a single galaxy or cluster you can point to. It is the sum of everything, the pattern formed by matter on the grandest scales. Picture a spider web stretched across the sky, but made of galaxies instead of silk. Along the filaments are chains of galaxies, linked together like glowing pearls, while at the intersections lie dense knots, clusters and superclusters, the great gatherings of galaxies bound together by gravity. Between these filaments are immense empty regions called cosmic voids, vast expanses where few galaxies reside, stretching for hundreds of millions of light years. Together, this lattice of filaments and voids forms the true large-scale structure of the universe, the cosmic skeleton upon which all smaller objects are built. The discovery of the cosmic web was not immediate. For much of history, astronomers saw only isolated points of light in the sky, stars within our own galaxy. Even when galaxies were recognized as island universes, the universe still seemed like a relatively uniform expanse. But in the late 20th century, as galaxy surveys began to map the three-dimensional positions of millions of galaxies, a revelation emerged. Instead of being spread evenly across space, galaxies were strung along immense filaments and walls, leaving behind huge voids. One of the most striking early discoveries was the CFA2 Great Wall, a sheet of galaxies extending 500 million light-years across. With each new survey, the picture became clearer. The universe was organized like a cosmic web, with filaments stretching across unimaginable distances. The underlying reason for this pattern traces back to the earliest moments after the Big Bang. The young universe was nearly uniform, but tiny fluctuations in density existed, imperfections in the otherwise smooth sea of matter and radiation. Over billions of years, gravity magnified these fluctuations, pulling matter into denser regions while emptier regions grew emptier. Dark matter, invisible yet dominant in mass, served as the scaffolding upon which this growth occurred. Ordinary matter, the kind that forms stars and galaxies, followed the contours of this invisible framework, pooling in the valleys of dark matter's gravitational landscape. The cosmic web, then, is not just made of galaxies, but of dark matter, filaments that bind the universe together. What we see, the glowing galaxies along the filaments, is merely the luminous frosting on an invisible cake of far greater extent. The scale of these filaments is astonishing. Individual strands can stretch for hundreds of millions of light years, and the entire web spans the observable universe, which itself is about 93 billion light years across. Each filament is not thin, but swollen with galaxies, gas, and dark matter, sometimes forming bridges between superclusters. The voids in between are equally vast. Some voids are hundreds of millions of light years wide, nearly empty except for a few stray galaxies drifting in the darkness. These voids, in their emptiness, are as much a part of the cosmic design as the glowing filaments, giving the web its striking contrast of fullness and absence. The cosmic web is not static, it evolves. Over time, galaxies within filaments fall inward toward clusters at the nodes, while the voids expand as matter drains away from them. This process has been unfolding for over 13 billion years, and will continue for billions more. In the distant future, the web will become more pronounced as matter continues to flow along filaments into the densest regions. Yet the accelerating expansion of the universe, driven by dark energy, will eventually freeze this process, isolating clusters of galaxies from one another as space stretches faster than gravity can pull. The cosmic web, as we see it today, represents both a history of growth and a preview of its eventual unraveling. To observe the web directly is a challenge. Galaxies trace its outlines, but they are like lanterns hung along the roads of a vast, unseen network. The true skeleton is the dark matter, which does not shine. However, its presence can be inferred through gravitational lensing, the bending of light as it passes through massive structures. By mapping these distortions, astronomers can trace the invisible filaments. Another method is to use the faint light from quasars' distant galaxies with active black holes as backlights. As their light passes through intergalactic hydrogen gas that lies along the filaments, it carries the signature of the web structure, revealing the otherwise unseen threads of the cosmic design. The cosmic web is not just beautiful, but essential. It determines where galaxies form, how they evolve, and where clusters collide. Galaxies are not randomly sprinkled across space, but born and nurtured within the filaments, fed by streams of gas funneled along these cosmic highways. Without the web, the universe would lack the organization necessary for galaxies, stars, and ultimately planets like Earth to exist. In a sense, we owe our very presence to the web's existence. We are not just inhabitants of a galaxy, we are inhabitants of the cosmic web, living within one of its glowing filaments, a thread that stretches across eternity. One of the most remarkable features of the cosmic web is how it mirrors patterns we find in nature on far smaller scales. The distribution of galaxies across billions of light years resembles the branching of neurons in the human brain or the filigree of fungal networks spreading underground. In both cases, efficiency governs structure, the need to connect points with minimal effort while balancing strength and stability. As we journeyed from the scale of stars and nebulae to galaxies, clusters, superclusters, and finally the vast cosmic web, the universe has revealed itself not as a place of chaos, but as a grand design, each layer building upon the next. We began with the familiar glow of stars, each a nuclear furnace burning across millions or billions of years, and followed them into the arms of galaxies, spiral, elliptical, irregular cities of stars bound by gravity and time. From there, we widened our gaze to see clusters of galaxies, immense gatherings stretching across millions of light years, held together by the unseen presence of dark matter. These clusters themselves became the bricks of even greater structures, the superclusters, sprawling continents of galaxies that hint at the scale of the cosmic stage. And beyond them, the cosmic web revealed itself as the ultimate tapestry, weaving filaments of light across billions of light years, linking the universe into a single interconnected whole. What begins as a single star above your head on a quiet night is, in truth, a gateway to a universe whose vastness stretches beyond comprehension. The largest things in the universe are not single objects, but the patterns that connect everything together. The galaxies, clusters, and filaments are not scattered randomly, but arranged into a structure that mirrors the rhythms of nature itself. From the branching of neurons in the human brain to the spreading roots of trees underground, the cosmic web is both unimaginably vast and intimately familiar, reminding us that the same laws that govern the smallest particle shape the greatest structures of all. For us, living on a small planet orbiting an ordinary star in a single galaxy, this perspective is both humbling and comforting. It humbles us because our place is so small, a speck within a galaxy that is itself a speck in a cluster that is one among countless others woven into the web of the cosmos. But it comforts us because we are part of that web. We belong to it, carried by its threads, connected by its gravity, shaped by its history. The atoms in our bodies, the elements that make our world, were forged in the stars that live within those galaxies, and through them, we are tied directly to the universe's grandest structures. In the end, the largest thing in the universe is not something distant and separate, it is the universe itself. In all its vast interconnectedness, a living fabric of galaxies and stars and voids, stretching outward in every direction. To drift into sleep with that thought is to carry with you not just knowledge, but wonder, the quiet realization that even in our smallness, we are woven into the very largest patterns of all.